Physics Bites,
Physics Bites,
a science podcast in English by the students of Notre Dame d'Ascension.
Hello and welcome to Physics Bites, the English language physics podcast of the students of Notre Dame d'Ascension here in Paris. A new episode this week. We're going to be talking about cosmic rays. We have two new experts from our senior class. They're going to present themselves and we'll get right to the heart of the matter.
Hello, I'm Noe Rojas.
So we have Noe.
Hello, I'm Luca Claudel.
And we have Luca. They're so expert in the field, they're actually giving me their last names as well. All right. So how about we get right to it? What are cosmic rays?
So cosmic rays are particles that travel through space at very high speed. And they're made of, most of them, protons. Mm-hmm. And other particles like helium nuclei or heavier elements like carbon and iron.
So the name cosmic rays, is that because they come from the cosmos?
Yes, from the outer space. They come from different sources, like when a star explodes, it creates a supernova. So most of them come from supernova, but also from existing stars like the sun. They.
So on that note, let's before we get to the origins of these rays, I think you guys talked about there are different kinds of cosmic rays.
Yes.
How many kinds there are?
So two.
Okay. Can you just give us a brief idea of what the two are, and then we'll go into where they come from?
Yes, no problem. So the first classification for cosmic rays is the primary cosmic rays. Okay. So the primary cosmic rays are those who are in the outer space. Okay. And who travel at a very high speed.
Right.
And
so by that you mean that they were created outside of the Earth,
yes,
very
exactly.
far from Earth, and they're just going in all directions, and some of them reach Earth. Okay.
Exactly. And when they reach Earth, we call them secondary cosmic rays, okay. Because they separate themselves in many particles, okay. And this phenomena is an air shower.
Okay, and this happens for what reason? Why are these secondary rays created when they reach Earth?
Because they interact with atmospheric particles,
right?
And they create all kind of new particles, like carbon-14, for instance.
Right. Okay. So basically, what happens? You have these very high energy rays coming from outer space, and when they reach Earth, the Earth is surrounded by an atmosphere, which is basically a large collection of molecules, air molecules basically, hydrogen, oxygen, nitrogen, etc. And you're saying that the collision between these primary cosmic rays and these particles, yes, that creates new particles.
Exactly.
And these are what you called secondary cosmic rays. All right. So let's get to the primary ones. You said that they are coming from outer space, from far away. Yes. What is creating these cosmic rays?
So we have different sources for cosmic rays. So we have the solar origin. Mm-hmm. So the sun emits cosmic rays that reach Earth. And these are mostly proton and electrons.
Why are these produced in the sun? What's happening in the sun that's producing these cosmic rays? Do you know? I know it's a very technical question.
Yeah. Well, isn't it fission?
Right.
Happened?
So basically, at the origin of all this are mostly nuclear reactions, yes, nuclear transformations, which create, amongst other things, lots of energy, which is where the energy of stars come from, but also these sort of secondary particles that are sent out into space, which are very high energy at so high speed. Okay.
Yes. So then we have a supernova that are considered one of the primary sources of cosmic rays. So it's the same process when a supermassive star explodes. It creates a lot of reactions, nuclear reactions, and those particles are thrown away at a very high speed. And so this is where most of the cosmic rays come from.
Okay.
Then we have neutron stars and pulsar.
Mm-hmm.
So neutron stars are dense remnants of massive stars. Of a massive supernova, and pulsars are a neutron star that rotate on themselves
Okay.
and throw particles at very high speed
And high energies.
and high energies.
So maybe we can take a little sidetrack on these neutron stars. Where are they formed? How are they formed? Are they common? Any ideas?
That's a good question.
So I know it's not your topic. It's more what we call star formation and this life of stars.
Yes.
But so they used to be normal stars like the sun, and then what happens at the end of the life of a star? Do you know?
Collapse.
Right.
itself.
So when it runs out of fuel, basically sort of expands,
Yes.
and then it collapses onto itself. And what happens?
I think
No.
that it trades like fog and little particles.
So it goes through a giant explosion,
Yes.
which
yes.
we call a nova.
Yes.
And if it's a big star with lots of that matter, it's called a supernova, right? And then most of the stuff is ejected out as dust particles and these particles, and then what remains sort of collapses on itself into this very small and dense star, which is really small but very, very dense, right? And it has very high gravitational forces. And if it's spinning, you call it a pulsar. Do you know why it's called a pulsar? It's a contraction of two words, pulsar.
That's a question I actually don't know, but maybe you can.
It comes from pulsating star, because when they start turning, they start giving out pulsations in a very regular interval, like X-rays, basically,
Yeah,
mostly.
yeah.
And we can detect it from Earth. That's how they were discovered. Okay. You talked about these particles that we call cosmic rays are remnants mostly of nova and supernova activity. Are they everywhere in space? Are we bathed in space, or is it like little particles here and there?
No, actually, they're everywhere.
Yeah.
Just thanks to Earth's electromagnetic field.
Mm-hmm.
There's very few cosmic rays on Earth.
Right, at the surface.
Yes, at the
Okay.
surface.
Okay.
There are cosmic rays basically everywhere in the
Okay.
universe.
So if we were further away from our planet, like for example where the space station is or something like that,
Yeah.
there's much more cosmic rays.
Yeah.
Yes, and
Okay.
and that's a problem like to plan a trip
Right.
to Mars because astronauts are exposed very much more cosmic rays.
Okay. So that's something we would have to. What about people in the space station? Do they have to be protected from cosmic rays?
Yeah, but actually, today they don't spend very much time outside of Earth's atmosphere,
Mhm.
so it's not very problem. But it will be a problem if we start to we plan to go to Mars,
Mhm.
because there the astronauts will be exposed to very high radiations,
Okay.
and
And
this
for longer durations.
Yes,
I
exactly.
guess. Okay.
900 days.
Right. A trip to Mars, we've worked it out to be about close to 3 years.
Yes.
We've never had a human outside of the atmosphere that long, I guess.
No.
Okay. So is there sort of like a classification of these sources of cosmic rays from lower energy to higher energy? Like between the supernova ones and the sun, and are there ones which are more dangerous than the others, more energetic than the others? What you guys research?
Well, I think that if they come, the further they come from, the less dangerous they are, I suppose.
Are you sure about that?
Maybe not, but no, maybe the size of the star they come from.
Right. So at least like the event that created it, right? So for example, as you guys mentioned, the solar cosmic rays
Yeah,
are not very high
No.
energy, but if it's coming from a supernova or even from black hole activity, then it's much, much more energetic, right? Some extreme cases of that. Okay. You also talked about Fermi acceleration.
Yeah.
What is Fermi acceleration? I guess it's again
So-
Luca is going to talk.
yeah. So Fermi acceleration is a phenomena where the particles that create the cosmic rays, are bouncing between the magnetic fields
Okay.
in the outer space,
Okay.
and every time they hit,
Like a planet with a magnetic field, or
yeah,
something like that?
or
a star.
or
Okay.
all the kind of stuff there is in the outer space, and when they bounce on a magnetic field, they take more speed.
Right. They gain energy from
They gain
it. Right?
energy, exactly, and we can imagine it like on a hockey field,
Mhm.
where the ice represent the space.
Yeah.
And how do you call
The
it?
puck.
Yeah, the puck represent the particle.
Right.
So every time the puck bounce against the wall, it takes speed,
Okay.
and it will bounce against another wall and take even more speed.
Right.
And
that's how they become more and more energized, I guess.
exactly. And they
Okay. And we
Yeah.
call this Fermi acceleration, I suppose, because it was Enrico
Fermi
who,
invented it in the 1940s.
right, who came up with a theory behind it.
Yes.
You also talked about magnetic reconnection and
Yes.
accretion disks for black holes. I'm just looking at the notes I took during your presentation.
Let me reply.
I think these were some of the more extreme cases. This is where different types of energy are released. Because you talked a fair bit about black holes and the rays that are coming from black hole activity.
Yeah, cause did I talk to that? Did I say that during the acceleration process?
Right. Yeah.
Yes. So the black holes are at the center of the galaxies, and they produce powerful jets that can accelerate particles,
Right.
and that can put them far beyond what other source of acceleration.
Okay. And so when you talk about accretion disk, because accretion disk is basically this disk of material falling into a black hole.
Yeah,
And because it's, especially you talked about black holes at the centers of galaxies, which are the most powerful and most massive ones, these are particles that are accelerated to very, very high speeds. And that's part of the reason they emit a lot of radiation. What are tidal disruptions? We talked about that as well, since we're on these supermassive galactic black holes.
Disruption.
It was something you mentioned when stars are falling into black holes. What were these tidal disruptions?
Isn't it when a star is torn apart, a black hole?
Yep.
And it produces high amounts of energy.
Right. So basically, this is all stuff which are consequences of the amount of the extreme situation that black holes engender. Okay. Maybe we can move on to. So this was mostly about origins of cosmic rays, their properties, and stuff like this. Maybe we can come back to how we detect them, and then we'll move on to what are some of the consequences of these and what the effects can be that have had on life and theories that are around it. So how do we detect them on Earth?
So on Earth, basically, we have detectors, ground detectors that are here to detect the amount of positrons that are arriving on Earth.
Okay.
And so this amount of positrons aren't only due to the energy emitted by the sun. So we scale the amount of positrons that are arriving.
Okay.
And then thanks to that, we can judge the amount of cosmic rays that are arriving.
But these are ground-based detectors, and you mentioned that cosmic rays are pretty much almost entirely blocked out by the magnetic field of Earth. How do we detect them on Earth then?
Because it's only the low energy cosmic rays that are blocked by the Earth's field. Okay. And the high energy cosmic rays can go through Earth's field.
Is that not dangerous for us if the high energy ones can go through?
No.
So actually, the Earth's magnetosphere acts like a shield,
right?
And the average dose that we get from the radiation on Earth is very, very much less than what we can get on in space. Sorry.
Okay.
And the primary cosmic rays, when they hit the atmosphere, they divide themselves into numerous particles. So,
which is this? What you're talking about here is the secondary.
Yes,
power.
Secondary. Exactly.
So, if I understand this correctly, the primary rays mostly are gonna get to the atmosphere, but then they're gonna collide with other stuff.
Exactly.
And so, what we can detect on Earth is almost only secondary particles, right?
Exactly.
Secondary rays.
Yes.
Okay.
So, yes.
Which have less energy, I guess, because the collision has sort of spread out the energy from those primary cosmic rays into lots of smaller ones.
So this is an air shower.
Okay, right. This is what you talked about, air showers. Can we see air showers?
Actually, yes. Actually, we can see. It's it's very much like an aurora borealis.
Right, which is a phenomenon we see because of, again, the interaction between the radiation coming from the sun and the Earth's magnetic field.
It's not the aurora borealis that you can see on the poles.
Okay.
It's only a phenomenon that's slightly smaller than them. Like compared to an aurora borealis, we could only see a few meters.
Okay. Okay. So we could see it, but it's not really as visible as some other phenomena, such as the aurora colors that we see in the atmosphere. Okay. What technology do we use to detect cosmic rays on Earth? Like, how do we do it? What does the instrument look like? What is it actually doing to detect the presence or the amount or the rate of cosmic radiation that it's receiving?
Like I just said, on the poles we can see it's called the fluorescence.
Yeah.
Which is due to the Cherenkov radiation. Maybe I can explain it.
Yes, go for it.
So, what's the Cherenkov radiation? It's basically when a particle that is moving faster than light is going through a medium like air. Mm-hmm. It emits a blue glow, which is like a sonic boom in light. Okay. And so, since this is mostly emitted at the poles, because it's where the cosmic show is the closer to Earth.
Okay.
We can detect them very, very easier.
More easily, yeah.
More easily, yeah. And thanks to that, we can judge the amount of...
Okay. So, just one question, because this is a question of Cherenkov radiation. You said when particles are going faster than light, how is it possible for a particle to go faster than light? What we learned in grade 10 was nothing can go faster than light, right? Yes. But
it's only in space where there is...
Right, in a vacuum. So what is the actual speed limit of anything is the speed of light in a vacuum. But we also learned that light goes slower when it goes into another medium. That was where we learned about refraction and all that stuff. Okay. So in any medium, so something can go faster than light in a medium, it just can't go faster than light in a vacuum. And so when it does go faster than light in whatever given medium, like you said, when we go faster than sound, we hear the sort of boom, what we call a sonic boom. We have the equivalent of that, which is not a sound, but is a blue glow. Yes. Okay. Where else? Do you know where else we see Cherenkov radiation on Earth? One of your classmates who recently did a podcast was Marion and Lily, who were talking about nuclear energy.
It's in the particle accelerators.
We also see it in particle accelerators, but in nuclear power plants.
Yes.
Right. Because there we have particles that are ejected at high energy in a medium that is not the vacuum of space. Okay. So basically, because these particles are super fast, we could detect them because they're going faster than light in a given medium on the surface of the Earth.
And there is also another way to detect them. So it's sorry, I'm searching the name.
Is it one that starts with M?
The GMEUSO project,
right?
Which is in space.
Okay.
And so it detects the cosmic rays that are arriving on Earth, but it's way easier for it to detect them because it have access to all of the cosmic rays that are arriving on Earth.
Right, because it's not absorbed by the atmosphere, right?
Yeah, exactly. So
measuring about
it can measure the low and the high energy particles that are...
Okay. So the idea would be that because we're protected from cosmic rays by our atmosphere, it's because most of it is absorbed by the atmosphere. So if you put it... or deviated. So if we're outside the atmosphere, then you can see those cosmic rays in much more abundance. Okay. Very good. You also talked about myography.
Yes.
What is myography?
So
this word word.
Myography, it's like basically like for doing radios. Okay. So a muon is a particle that has that can go through many medium.
Okay.
And medium, it can go in deep medium way deeper than X-rays can, and so it basically have the same abilities than X-rays.
Okay.
But since it can go in deeper medium, we use them to detect dangerous. Sorry.
Okay. Yes.
Yes. So myography is based on muons. So what are muons? Muons are particles that are basically like X-rays, so that can go through mediums.
Okay, just so we're clear, muons are a fundamental particle.
Yes.
They sort of resemble electrons, but they're like a bit heavier. They have some properties that are different. Where do they come from? What is producing muons?
It comes from the cosmic rays.
Right.
The secondary cosmic rays.
Right, so they're part of these air showers, as you call them.
Yes, exactly.
Right. So, and what is so specific about muons, which allows us to use them to detect cosmic rays, measure cosmic rays, and do what you called myography during your presentation?
So muons have the ability to go through very deep mediums.
Right.
So we use them like to detect chambers in pyramids.
Right. So they interact very little with material, so they can go very easily without being absorbed or okay.
And so how do they help to detect cosmic rays?
Mm-hmm.
So as Luca said, when primary cosmic rays arrive on Earth and they meet with the Earth's shield, they create secondary cosmic rays, and so there's a percentage of each particles that are emitted by the primary cosmic rays.
Right.
And so when we scale the amount of muons that are arriving on Earth, we can calculate the amount of cosmic rays that went through the Earth's shield.
Okay, that sort of gives us an idea of how much cosmic rays were incident in the first place to create this. Okay. You also guys talked about some of the consequences of that for life on Earth. Because in and of themselves, cosmic radiation could be dangerous, right? These are high energy particles. They can create ionizing energy, which could lead to radioactivity. Yeah. They can burn. They can destroy a lot of things. So there are consequences on life on Earth.
Yeah.
Luca.
So, the main consequences will be on the human body.
Okay.
So, some astronauts that have spent time in the ISS reports that they had experienced, sleep disorders or mild cognitive declines. And we have done on Earth some experiments on animals like rats. And how can I say that? Where they faced high amounts of cosmic rays on them, and we have they experience lots of problems because cosmic rays attacked the DNA particles, so they break
the chemical bonds, I guess,
chemical
in the
bonds,
DNA, they create mutations.
Exactly. So this leads to mutations.
Right.
And some hypotheses actually suggest that some supernova explosions could have influenced the life on Earth.
Right. So we're talking about evolution and natural selection,
because it's linked to the mutation. So linked to so the supernova. The cosmic rays produced by the supernova could have influenced some mutations that happen on Earth and led to the natural selections on Earth.
So it's an interesting idea to think that supernovae, like very, very far away, they would provide the source for mutation. And we think that mutations are bad, but mutations are actually necessary for evolution, because that's what creates new sort of alleles and new genes which can be beneficial and lead to new species. To think that life on Earth was amplified, I guess, in some ways by cosmic radiation coming from far, far away, supernovae and stars going to their death. I don't suppose we on Earth actually have any problems today because of cosmic radiation, right?
No. Actually, there is a way to measure how much we are exposed to cosmic rays. So the unit is called the millisievert. So the sievert is a unit to measure how much radioactivity we are exposed.
Right.
And on Earth, the cosmic rays, those that we receive from outer space, is about 0.3 millisievert.
Okay.
To give you an idea, in the space station, they receive about 150 to 200 times more cosmic radiation than we do on Earth. So that will be 160 millisieverts a year. And we talked about trip on Mars.
Right.
So a trip on Mars would take much more time, like 1 or 2 years, and astronauts would receive 600 to 1,000 millisieverts.
And just out of curiosity, do you know what the limit is for human safety? Or at least each country sort of chooses its own limit, but what do we think about in...
It's about 1,000 millisieverts.
Okay. Likely. So there's basically what you're saying is that the amount of radioactivity that we receive on Earth because of cosmic rays is almost negligible.
Exactly.
Compared to other natural sources of radioactivity.
Yeah.
And is it true that if we fly in an airplane, we're more exposed to it? To cosmic rays?
Yeah, that's true. And at an altitude of approximately 1,000 meters, 10,000 meters.
Right.
So the pilots of commercial flights receive about 2 or 3 millisieverts a year.
Okay. Which is one of the reasons, if I'm not mistaken, why pilots and air hostesses and air hosts don't work every day of the year, right? Outside of the fact that it's not good to be working that much, but because they have to also survey how much cosmic radiation they're actually receiving.
Yeah.
Okay.
That's true.
Very good. You also talked about, so for these astronauts that we send into the space station, do we give them some sort of protection for this, or are they just sort of left up to themselves to deal with the consequences of it? Is there a way of like protecting, like shielding a person or a space station or a space vessel?
Yeah, so actually now we are working on better ways to protect them, but today aluminium is used for shielding them, but we are working on materials rich in hydrogen, such as polyethylene, that could protect them much better, because cosmic rays are mostly high energy protons and heavy ions, and the hydrogen that materials like polyethylene contain, could receive these particles and spread the energy into the material and absorb the energy. Not all the energy, of course, but it could absorb more energy than aluminium or those kind of materials.
If I'm not mistaken, I think that's sort of also similar to how solar creams sunblock works. They kind of get that energy and it's absorbed into these chemical bonds that the molecule has, and it's sort of
hydrogen is
because it has a very high. I guess the resonance frequency is corresponding to a lot of these kinds of radiations. Okay, so maybe we can move on to the very final part of it that you talked about. You mentioned some sort of a link between maybe detecting dark matter and cosmic radiation. What's that all about?
Basically, let's go from how we detected to the hypothesis. So the IMS-02, which is the detector which is in space, has only gone to detect the amount of positrons that are arriving on Earth. Okay. And so there were some estimations about the amount of positrons that should arrive on Earth, but the amount that really arrived on Earth was way higher than the one expected. Okay. So there is one hypothesis, which is that dark matter, which is only a hypothetical matter. Right.
Which means that we haven't actually detected directly dark matter, but we have a good idea that there should be something that resembles that somewhere. Okay.
And so the hypothesis is that dark matter interacted with the cosmic rays that were arriving on Earth. And so while interacting with them, it produced some positrons. And so this could be one of the explanations of the amount of the extra amount of positrons that arrive on Earth.
Okay.
And so if this hypothesis is true, it might prove the existence of a fifth force.
Okay.
which could explain all the interactions between normal matter and dark matter.
Okay. So now we're really at the cutting edge of new ideas in physics. But it's interesting to think that this sort of very natural cosmic phenomena, which is this cosmic radiation, cosmic rays, can actually be leveraged to use to detect something which is much less known, which is dark energy. Okay. I think we've gone through most of the topics you guys brought up. I think, Noe, you have any?
Yeah, just
one or two things.
Cosmic rays are also helpful to test general relativity.
Oh, okay.
Since we only could observe the effects of general relativity on normal energy, on normal energy particles, but we think that it might not act the same way with high energy particles. So it could lead to review the general relativity with high energy particles.
Okay. Again, that's closer to sort of very more modern ideas and cutting edge physics. Okay. I think we've gone over most of the topics, right?
Yes.
Maybe as usual, as I ask all your classmates, I can ask you guys the same question. What did you find most interesting, most call it striking in all the research that you did? Just because, especially, I guess, Luca, you're not doing physics. You haven't done physics since 2 years ago.
Yeah.
Even though you have been doing this in other class. It's okay. You're forgiven. You're forgiven because you're doing well in your other classes. And Noah, you're doing physics, but this is not the kind of physics we do anyways in class. So what did you guys find particularly interesting, maybe difficult, striking in the research that you did? Noah?
I'll say that just discovering the fact that there are cosmic rays that actually influence our life and influence how Earth have been shaped.
Yeah.
And also the fact that it could show the existence of a fifth force, because nowadays we only learn about the four
fundamental forces, interactions and stuff, yeah.
And so I thought that the fact that we only discovered it like 1 century ago,
right, or even less,
and that nowadays we could imagine the fact that there could be a fifth force, and that for decades we imagined dark matters, and it could also explain, could also prove the existence of dark matter. I feel that I didn't know about it 2 months ago, and now.
I think it's interesting to note that the more we learn about space, the more we realize that empty space is anything but empty, right? There's stuff going on, we just can't see it, or at least see it easily, but doesn't mean that there's nothing there. Luca, what did you find?
For me, first of all, it was, as you said, I'm not doing physics anymore, and it was a way to show me that physics has still much to teach me. And so I'm very interested in the outer space question,
right?
And studying what is going on up there really interests me. And so learning about those particles that travel actually through very, very, very long distances
and long durations, like billions of years, yeah.
Triggers me, because we could only dream of seeing all what those particles are seeing actually in space, and they come to Earth and they actually reach us. So
and have an influence on life. Right?
So I found that a bit crazy that those particles that have been on space for millions and billions of years have an actual influence on our daily life.
Right. I think that's one of the reasons why space is always something that intrigues everybody, whether we do science or not. It's just that there's so much craziness out there, and the way that the most far-fetched stuff can influence life and our existence is always interesting to learn. Okay, so thank you very much for your very interesting presentation on cosmic rays. I hope you guys enjoyed it as much as I'm sure the listeners are going to enjoy. Thank you, guys.
Of course. Thank you. See you.
So, that is Physics Bites for this week. We hope that you enjoyed this episode, and we would love to hear what you thought about the topic in the comments section. If you did enjoy the show, then subscribe to our podcast, share it with your friends, and be sure to leave us a 5-star rating on whatever platform you're listening on. And more important than all of that, come back soon for a new episode.